Hi everyone, my name is Muna and I am a PhD student at Durham University. Today I'm presenting our paper which is about distillation of a human-object interaction context for action recognition. This is the agenda of my presentation. First, I will give a brief introduction about complex scenarios of human-object interactions. Then I will explain our proposed network, which is called Global Local Interaction Distillation Network. Then I will move to show some experiments that we conducted to compare our model with the state-of-the-art models. In the last part of my presentation, I will cover different designs of teacher networks and I will end my presentation with a conclusion. In our work, we focus on human actions that involve interacting with some objects. There are many complex scenarios which are challenging to be recognized. For example, a human can interact with the same object, but doing different actions. Also, different objects can be used to perform the same action. Additionally, different objects present around a human could confuse model predictions. And the state of humans and objects are changing over time. For example, a human can hold an object and release it at any time step, then interacting with another object, which makes identifying correct interactions very challenging. For all these scenarios, the contextual information about the interaction is giving important cues which helps recognize actions. So we propose to use different views to gather these contextual information. The first view is the global view, which encodes human and human-object relations over time. We can consider it as a temporal relations. And the second view is the local view, which captures human-object relations at a specific time, and we can consider it as spatial relations. And in order to construct these contextual views, we use one of the graph networks called graph attention networks, where human and objects are nodes in the graph, and the edges are learned during training. And after we construct these views, we use knowledge distillation to transfer the knowledge between these views and by considering student-teacher network design. We validate our proposed model on two public datasets, including Shiraz and CAD 120. And as we can see here, some examples of human-object interactions which are present in these datasets. Some of the examples are including holding a laptop, washing a window, and holding a box, and etc. In these two tables, we can see that the results of our model comparing to other prior works, and also we can see that our model outperforms other approaches, including models that are not considering the human-object relations like I3D, and also compared to graph-based models which implicitly consider one view of interactions such as search. And in our experiment, we showed that by using two different backbones, including I3D and SlowFat, we achieved the best results. We also conduct some ablation experiments as in table 3 here. And by considering different settings, such as using only one view, including spatial or temporal relations. Also, we conduct experiments to investigate which of the views can play the role of the teacher. Here, by considering the local view as a teacher, or the global view, which is the temporal relations between human object interactions, as a teacher. And we can see that the temporal view, which are global teacher, achieve the best results in these two datasets. However, in Shiraz, when we use I3D backbone, which considering a less number of frames, the local view achieve the best results. Also, from table 4, we can notice that our model offers more informative views about interaction with less number of nodes, and even without any human object abstract information, such as edges, which are the union of both objects and the human in a stage model. Here we show two different examples of human-object interactions from CAD 120 dataset, and we can see that when we use one view, the interactions are misclassified, and by using both contextual views, including local and global views, the actions are identified correctly. In the last part of our paper, we investigate the design of the teacher network. So, we conduct different experiments by considering the local graph at a frame as a teacher. In this case, we will have multi-teachers to distill the knowledge from. And when we train our student network, we are taking the mean of the distillation loss in addition to the cross-entropy loss, which is the classification loss. And as it's seen in table 5, this is the results of our experiment. We can see that using multi-teachers with 30 frames is providing more contextual information to the students than using less number of frames, such as 15 frames. We also observed that considering the spatial relations based on single teacher at a video level produced the better knowledge, which can be distilled to the students. In conclusion, we can see that contextual information is very important for recognizing human-object interactions. Also, using different views of interactions with knowledge distillation is improving action recognition performance because long-term and non-local dependency between human and objects across video frames can be captured. Our future work will explore self-supervised approaches for identifying human and objects and their relations and interactions in videos. Thank you for your attention, and please contact me if you have any questions.